Saxon Advanced Mathematics. That sounds so amazing, doesn't it? Makes you feel smart, I hope, every time I say it. Lesson 2. You guys, this is another really rigorous lesson. There's a lot of information. The book has a couple really dense pages of pictures and crazy sketches. We're gonna hit the highlights. There's a lot of information here, so use your book as a resource if you get stuck on something or if some word gets thrown at you that you don't remember. Look it up in your book. What I'm gonna do is I'm gonna focus on formulas. Gracie is now chasing one of the cats, which usually never happens. What are you doing? She's like, you know, jumping. What are you doing? Are you all right? Why are you disturbing poor Luna? Okay, that's under control. Okay, so here's something that I don't know if I mentioned the first time. Gracie has things to say. Use the covers of your notebook to write down your formulas. Now, if you're like me, the inside front cover of my notebook is plastic, so that won't work. But the back cover is cardboard. So I can write on the front and back side of my back cover. And it's a great place to keep your formulas handy so that when you're doing your homework, you don't have to go shuffling around and try to find them. It will also lead you to memorize them because even flipping around your book to the back page is enough of a pain that sooner or later your brain will just go, it's easier just to remember these than to flip every time. So eventually you'll break yourself of even that habit of looking at your covers and you will be memorizing them, which is our end game, right? Okay, so let me just dive in. I'm gonna focus on the examples. There's more information in the book if you need it. The first formula I'm gonna throw at you is a volume formula. Remember, volume is a three-dimensional measure, right? Lines are one dimension, so like perimeter or circumference. Area is two-dimensional, and volume is three-dimensional. So to find the volume of an object, we multiply the area of the base times the height. And to write that in its shortest abbreviated form, that's how I'll do it. Volume equals area of the base times height. Okay, so when we're doing these, usually finding the height is super easy. It's just, you know, it's in the picture or it's in the words. It's not a big deal. And the area of the base is where we usually run into drama. Example 2.1 is a perfect example. This is the type of shape that we have. And by the way, when you're doing these problems, I think the way to start is always to draw the picture. It just helps you notice things about it that you wouldn't otherwise maybe pay attention to. We get a picture of the three-dimensional image. I'm drawing them in the opposite order. John does that one on the right. I put it on the left. It doesn't really matter. And here comes the other picture. And I will read the problem to you in just a second. Copy with me. Okay. One more. Okay, so what did we draw? Okay, this is the three-dimensional object. This is the base of the object. If we could pick this up and look at the bottom of it, this is what we would see, or the top too. What this kind of two-part diagram does is it allows us to get a really good picture of the overall object, and then we kind of zoom in on the base because we have to find the area of the base, so we need all the details about that. This one we can see is some sort of a quadrilateral. We can see right away that it's not a perfect square, it's a rectangle. And then we have a semicircle attached here. This is the radius of that semicircle. Remember that the radius is the distance from the center to the edge of the circle at any point along the circle. So if the radius is 3, that also tells us that this could be a radius, so that's 3. And this could be a radius, so that's 3. Sometimes we won't know the length of this side. Here, it's given to us. But here we just proved it. We used that radius to calculate up and down. All right, let me read you the problem. The base of a right cylinder, 10 centimeters high. Okay, so that tells us that this dimension is 10. Find the surface area of the right cylinder. Dimensions are in centimeters. Okay, so we're not doing volume in this problem, which is weird because they gave us the volume formula, but that's okay. We're gonna do surface area. Surface area I always think of is like you're gift wrapping it, only it's magical wrapping paper, so you never have to overlap it, even the tiniest bit. It's just a perfect covering. I guess it's kind of like if you were covering it with contact paper, if that's a thing you ever do. But anyway, we're talking about finding the area of all the sides. So with surface area, we usually add up the area of all the different sides, okay? I'm gonna write that down. It's not exactly a formula. Okay, so to find the surface area, we find the area of each of the surfaces, and then we add them all together. So what we do is we take out a pair of imaginary box cutters, and we start cutting the box open. What I'm gonna do first is I'm gonna cut off these two, what I consider to be mailbox shapes, kind of like that. To me, that looks like a classic mailbox. I have encountered a few students, most of whom are male, that think it looks like a toilet lid. I mean, that's fine. Either way. So we have two of those, right? Because we're gonna cut off the top and we're gonna cut off the bottom, right? So we'll do that, and then that piece that we have left that's gonna be kind of open, we're gonna cut that along one edge. We'll cut it along this edge, okay? And then it's gonna have this whole length, right? Because we cut it down here. So this all opens up now, and we have a long skinny strip of cardboard. There will be this long length, and then, let's see, we're cutting it like right here, right? Because the hoop is over there. So we'll have this long length like this, and then there will be a fold, and then there will be another section. We'll get into that more, but I want to do the other part first. All right, so how do we find the area of this hoopy bit? Well, we look at this picture and we find the area of the picture. We see that this thing is made up of a quadrilateral and a semicircle, okay? So in order to find the area of this whole shape, we have to find the area of those two components, add them together, and then multiply by 2, right? Or add it twice, however we choose to do it. All right, the area of the rectangle, that's length times width. And we can see here we've got the numbers all sorted out for us. It's 5 times 6, and that's 30. Okay, I'm drawing myself a little table here. The semicircle, oh, let's see. The area of a circle is pi r squared, but we want a half circle, so we divide it by 2. That is pi, which is 3.14, times the radius squared. The radius is 3, so that's 9, divided by 2. And then what I'm going to do is I would like to make that denominator go away. This is what my brain's doing. It's saying, I don't want to divide this by 2. That's just one more step. I remind myself, oh, I'm going to have to multiply this by 2. So why not do that now? And then that will cancel my denominator. That reminds me that I have to double this as well. So I'm going to change that to a 60 right away. Okay, so this represents the rectangular component for the top and the bottom. All right, and then this represents the semicircle part for the top and the bottom. So now it just becomes 3.14 times 9. I'm going to use my space up here to multiply. 36, 12, 13. 2 decimal places. All right, so 60 is 2 of the rectangles. 13.26 is 2 of the semicircles. Right, so together, the 2 mailboxy things equals 73.26. That's the area of these 2 surfaces. I'm just double checking my calculation. Hang on, I'm just trying to find my 5 times 6 plus pi times 9 over 2. That's correct. Well, something's awry, but let's carry on. Now we need to find the area of this rectangular bit, okay? We know that it's 10 high, because we were told that right there. 10 high, and now we need to know this length, okay? So let's look at our cardboard here and imagine this part would be the first smooth bit. There's no folds in that. That relates to this. How long is it? Well, it's 5 on the top plus 5 on the bottom, plus this is the semicircle. So we need the circumference formula divided by 2. So the circumference is pi 2r. So when we divide it by 2 for a half circle, it's just pi r. So it's 3.14 times 3. All right. So that's how we get this length, is we have to find the perimeter / circumference of all of that. And then we have to add the 6 at the end, right? 5 plus 5 plus that plus that. Okay, so I see what I did wrong up here. I got crazy in my multiplication. 9 times 4 is 36, carry the 3. 9 times 1 is 9, 3, 12, carry the 1. 3 times 9 is 27. Right? Plus 1 is 28. Add that to 60. Okay, so I multiplied wrong. And so now I'm going to add, so now 28.26 is what I got for my multiplication. I add that to the 60, and my number is 88.26. Okay, that I like better. All right, so I've got this all figured out here. This long side is equal to all of these pieces added up, and so I have to get a total on that. 5 plus 5 plus 6, that's 16. 13 times, or 3.14 times 3. Now I'm multiplying pi times the radius. 3 times 4 is 12. 9.42. Right, I added all the straight sides together, and now I'm adding, this is the curved side. So this becomes what, 25.42. Okay. And then this is, I often forget this step because we are doing so many steps along the way. Now we multiply this by the height to get the area of this. So it's 254.20, right? I just moved the decimal place over 1 because I'm multiplying by 10. Now I add the area of the two mailbox bits plus the area of the rectangle together for our total surface area. 8 plus 4 is 12. 8, 9. 342. Now John's off by a few hundredths of a decimal place from me. His answer, this is my answer. $342.46. Maybe you guys saw where I made a little mistake. I didn't catch it, but John's answer is 342.53. So I'm off by 7/100ths. I'm gonna call that good enough. I probably could go back and find out where I went awry. I'm pretty sure I went awry. But the process is right, so forgive me for my mistake. All right, that makes sense? That's surface area. Here's another surface area problem that we're gonna dive into with example 2.2 before we go on. This one is fun. It is like a three-dimensional plus sign. And then it's like this. It's really fun to draw, so draw it. This is one of those things that we can do to make the homework a little bit more fun, is if you draw the picture, it's kind of fun. Get it to come out right. Takes a little practice, but hey, that's what we're here for, right? Okay, yeah, kind of. Now we put in the numbers. This dimension is 6. And then everything else, all of these sides are all 2s, which is very pleasing to me. 2, 2, 2, and 2, 2, 2. So again, we're doing the surface area of this. It tells us that, the instructions tell us that this is a right prism. A prism means that it's a three-dimensional polygon. It's got straight sides. Right means that all the angles are clean 90-degree angles. Whenever you see this word right, just know John just made it easier for you. By calling it a right shape, it means that everything's square and even and you don't have to deal with any sort of like tapering sides or something like that. That is a blessing. So whenever we see the words right, we are happy because we know it makes it simpler. Okay, we're gonna do the very same thing. We're gonna find the area of the top and the bottom. We're gonna cut those off with our box cutters. And so we're gonna have two objects like this. And then we're gonna have one big long rectangle. That is what we have left. Imagine the top coming off, imagine the bottom coming off. Imagine cutting along one of these edges, let's say right there. We take our box cutters and cut it open. And now we have a big long piece of cardboard that has lots of folds in it. We'll figure that out later. But this is the side piece of all of that. Sometimes this is called the lateral surface area. And in some problems, John wants us to simply find that. Okay, if he asks you to find the lateral surface area, he's saying cut off the top, cut off the bottom, and throw them away. You don't have to deal with those. Then just cut open what's left, lay it flat, and find that. So that's a different word. Let's see. Now this one he asks us to find the surface area, and that means all of it. That means we include the top and the bottom. Okay, so we start with this one. We know that each of these is a 2 by 2 square, right? So we have 2 times 2 for each one of these little squares, right? That's how I chose to think of it. is I broke it up into these little squares. Each one's 2 by 2. There's one in the middle. So if we multiply that by 5, that should give us the whole surface area. And then we'll multiply it by 2 because we have a top and a bottom. Okay, so that means 2 times 2 is 4, times 5 is 20, times 2 is 40. I put a squiggle under it because that's the final answer for the first part, right? Now we're going to do this lateral surface area. This I kind of like because there's no semicircles. And multiplying by pi always makes it so much harder. So we just have to figure out, we know that there's 2 inches in every fold, so we just have to figure out how many sections of 2 there are. And we're just gonna start here, which is where we said we cut it. And we're just gonna go around and add up the number of 2-inch sides that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 2-inch segments means that this is 24 inches long. Okay, let's just go through the logic of that again. We cut it here, so we're going to start counting at this point. And there's a cat on my table. He's probably going to come and lie on my notebook, to be perfectly honest with you. Look, there he is. Hi, Luna. This is Luna, my all black little man. It's smoky outside today, so he doesn't want to go out, but he's curious. Okay, ready? Let's go. We're going to count again. Every single one of these is 2 inches long. So once we get it counted, then we'll multiply our total number of sides by 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I'm back up there. Okay, so 12 times 2, that's 24 this way. And then how long is the cardboard this way? That's 6 inches. 6 times 12, or I'm sorry, 6 times 24 equals 144. That's the surface area of this, okay? So our total surface area is 184. Oh, I didn't put the unit on the last one. These are just called units, so we can put units squared. Sometimes John just doesn't even tell us what they're measured in, he just says units, and we can use that as our unit. The last problem was centimeters, so this should say centimeters squared. My bad. All right, if John would have asked us in this problem to find the lateral surface area, not the whole surface area, our answer just would have been 144 units squared. Okay, so if he asks you to do the lateral surface area, even though that phrase is uglier, it's easier. It means less work. Okay, moving on. Cones and pyramids. All right. The idea with a cone or a pyramid here, let's start with a cylinder. A soup can. Think Andy Warhol. You know, he's the artist that did a painting of a Campbell's tomato soup can and shocked the world. Okay, if we were finding the volume of this, the volume of the cylinder, which is what we call this shape, we would do the area of the base times the height, right? That's our basic volume thing. What if we wanted to do a cone? Let's say that's the very center of the top of the cylinder. What if we wanted to do a cone? Right? We don't want the volume of the whole cylinder. We want the volume of this cone that's buried inside. What we do is we take this same formula, but we multiply it by 1/3. I'm just going to abbreviate it here, right? So this is the same as that. We just multiply it by 1/3. And what that does is say, basically, in order to get from the cylinder to the cone, we're going to have to whittle away some of this excess, right? We don't want all this extra part. We're gonna whittle it away. I imagine it like a bar of soap. You know, those soap cutting videos, think of that. We're gonna whittle it away, and what we're gonna whittle away is actually gonna end up being 2/3 of this original outer shape. And 1/3 is what we'll have left to be the volume of the cone. All right, and that works for pyramids too. All right. Let's do a problem. And this works for pyramids. The difference between a cone, I said a cone or a pyramid. A cone is based on a circle. A pyramid is based on a polygon, okay? So I think our example is a pyramid, so we'll do that. The base of a cone is shown. The dimensions are in meters. Okay, technically, well, I'll show you the picture and you'll see. If the cone is 6 meters high, what is its volume? Okay, so let's look at the picture of what this thing is shaped like. And we see it's actually a hybrid. It's part cone, part pyramid, because this is what the base looks like. It's rectangular on the left, and it's a semicircle on the right. The radius is 1. This is 2. This is 3. Okay? That's the picture that John gives us. And then he draws a picture of the whole thing for us, and it kind of goes like this. That's a little wonky. But you can see what I'm saying. This is the curved end. And then there's the straight, right? So then our dotted line is like that. And if we wanted to, we could draw these lines to help us see through it, right? That's the semicircle that's going around like that. All right? So this is part pyramid, because the pyramid is on the straight-sided object, and it's part cone that's on the rounded part. All right, so we're supposed to find what? The dimensions are in meters, and the cone is 6 meters high. That would be from there to there. Okay, meters. All right, how are we going to find the volume of this? Okay, well, there's our formulas right there. So what we're going to do is we're going to find the area of the base, and we're going to multiply it by the height, and then we're going to multiply the whole thing by 1/3. So I'm going to write that down. Volume equals 1/3 times the area of the base times the height. This is easy to find. This is where we're going to have to do our work, right? So let's find the area of the base. All right, it's got a rectangle and it's got a semicircle. I always draw my semicircles like that. It reminds me to cut the formula in half, honestly. That picture helps me remember that. All right, the area of the base, that's length times width. That's 2 times 3. That's 6. Area of the base, that is pi r squared, and then we need to divide it by 2. So in our case, it's 3.14 times our radius squared is 1. 1 times 1 is 1. Divided by 2. Okay? And so now we just need to figure this out. 3.14 divided by 2, it goes in there once. We get 11, that's 5 times. And with division, you put the decimal straight up. So that's 1.57. Oh, yes, 1.57. is the area of our half circle. So now we add together 7.57. If you want, you can add the 2 decimal places so that it's easier to line everything up. That is the area of the base. Oh, it's a lot of work just to get this, right? So now what we do is we take this and we plug in here. Volume equals 1/3 times 7.57 times the height, which is 6. All right. Oh, that's looking good. I'm going to cancel before I multiply. I always try to make my numbers smaller before I make them bigger. So I'm going to reduce that, change that into a 2, which will be much easier to deal with because I don't have to multiply and then divide. I can just double it. And I can pretty much do that in my head, right? So I'm going to add this against itself in my head. I'm going to add 7.57 plus 7.57. So that's a 4, 14, carry the 1. The 2 5s make 10 plus 1 more is 11. Carry the 1. 2 7s make 14 plus 1 more is 15. My unit is meters. And my dimension will be cubed because we're now in volume land. So 15.14 is my final answer. Yay, John agrees. Okay? So when we're dealing with cones or pyramids, it's just this one extra step of multiplying by 1/3. All right. Oh, are you still with me? We have a long ways to go still, you guys. These first lessons are murder, and I don't blame you if you want to just quit and go back to being a summer student. Because this is long and it's hard, but it'll get better. I promise you we're not going to go on like this forever. Okay, surface area of cones. This is not something that you're going to find yourself working on every day. We're not going to build on this. It's kind of a dead-end topic. I'm not going to give you a bunch of information. I'm just going to jump into the problem. What we have here is a very flat cone, which is kind of fun. And this is the front edge of it. That's the back edge of it. So the center comes down like this. And then pretend that's perfect. All right, it comes down to the very middle and it makes a straight line. The radius of the base of a right circular cone is 8 inches. The radius is 8, so that line right there is 8. And what did I just say, inches? No, centimeters. Put my unit to the side and circle it. The slant height of the cone is 10 centimeters. This is the slant height. It is the length of the outside of the cone. The symbol we use for it is L. Don't ask me why. That equals 10 centimeters. I'll give you the formula in just a second. All right. So how do we figure out the surface area of the cone? We'll need the circle, and then we'll need the curvy bit, the funnel bit. Find the surface area of the cone. Okay. So just like any surface area, we'll need to find the area of the circle, and then we'll need to find just the coney bit, right? Like the megaphone, if you picked it up, pretend there's a tiny hole in there. If you picked it up, that would be the part that was like the megaphone. All right. The circle is easy to do. We know the formula for the area of a circle. It's pi r squared. We don't have to divide it in 2 because we need a whole circle. We don't need a half circle. So that's 3.14 times the radius squared, which is 64. I want to make sure I'm reading that right. It's really dark today because of the smoke. Yeah, it's 6, not 8. Oh wait, I just looked at the wrong problem. No, I was right. It's 8. It's 6 in the next problem. Okay, pi r squared, it is 64, right? Because 8 squared is 64. So that is the area of that much. Now, how do we find the area of this cone thingy? It's pi times the radius times the slant height. All right, so I'm going to write this down. The area of a cone equals pi times the radius times that, where L equals the slant height, which is that bit. Okay, add that to your formula collection in your notebook. Pause me while you write it down. And now we'll go ahead and calculate it. So for this one, it's 3.14 times the radius, which is 8, times the slant height, which we were told was 10. Okay, so now all we have to do is calculate it. What John does in this problem, and I like this, is he says, let's not bother multiplying through by 3.14. Let's just leave that as the symbol pi. We'll simplify the other numbers, but we're not going to multiply that through. So I'm going to work it the same way so that you can see how we would do that. It's easier this way. It's less fussy multiplying and adding. I really like doing a problem where we just leave the symbol pi in there. What I recommend that you do is when you're working a problem and you realize, oh, should I multiply by pi or shouldn't I have a decision to make? Go look in the solutions manual and see how John presents his answer and then make your work match to his. So that's what I did. I just glanced at the answer. I didn't spoil it for myself, but I just said, oh, he left it with pi in the answer. So I'm going to do the same. So I don't have to multiply this through. I can just say 64 pi is the area of the circle. And then I'll see this one is 80 pi, right? That's pi. This is pi. So I just multiply those two. That's the area of the coney bit. And now I add 144 pi centimeters squared. Surface area is 2 dimensions. That is my final answer. John agrees. All right. I like this because we're still using the formulas and understanding the concepts just as well. We're just saving ourselves some fussy arithmetic, and I'm all for that. Okay. More. Sorry, there's lots more. I'm going to find out how many problems there are in all. There are 8, so we have 4 more to go in total. Okay, the volume of a right circular cone is blah, blah, blah. Okay, here's what we're going to do. Let me draw the picture first so you can see it. Here's our cone. Here's the center of the base. Here's this coming down. There's the radius. This is at a right angle. That's why we call it a right circular cone. The volume of the right circular cone is 6 pi. We don't usually get the volume. That's usually what we're going for. But this time we're told the height of this right circular cone is 2. And we're working in centimeters. Find the radius of the base of the cone. Whoa. That's crazy, right? Okay, so what we have to do in this one is we have to work backwards. We're given what normally looks like the answer, the volume, and we're given one of the components and we have to go backwards to find it. So let's work with our formulas first and see what we can get. The volume is going to be equal to 1/3 times the area of the base times the height. Okay, so now we can substitute this in. We know the volume is equal to 6 pi, so I'm going to write 6 pi equals 1/3 times the area of the base, And we know that in this case, the area of the base is pi r squared, right? Because it's a circle. So we can write, it's 1/3 times, I'm gonna put it in parentheses to help keep it neat. Pi r squared times the height, which we know is 2. All right? So this is how we solve for one of the missing pieces. We take the answer and we plug it into the formula along with any other numbers we know, and then we back up from there. So 6 pi equals 1/3 beautiful. Okay, so from here what we can do is we're multiplying and multiplying. So I'm going to say let's divide both sides by pi. Let's just get rid of that symbol right away. Okay, so all of this is over pi, and all of this is over pi. So what that's going to leave us is, flipping, six equals I'm writing it in the same order. We have 6 equals 1/3 r squared and 2 r squared. Okay, and these are all being multiplied together. All right. I want to get that r by itself. So what I'm going to do is I'm going to multiply by the reciprocal of these other pieces. So I'm going to multiply this side by 3/2. That will cancel that and cancel that. And then I have to multiply this side by 3/2. 6 divided by 2 is 3. So now I get 9 equals r squared. Oh, I like that, don't you? So our final answer is that the radius of this thing must be 3, and our units was centimeters. Nice, right? This is a very standardized, testy way to try to confuse students on this topic. When they give you the answer and you have to use the formula to work back in to find one of the components. John, you can't fool us. We're too wise for you. Example 2.6. The base of a regular pyramid is a square with each side measuring 4 centimeters. All right. Pretend that's perfect. I like drawing pyramids, they're fun. Okay, so it's a pyramid because it's based on a polygon. Pyramids and polygons, cones and circles. All right, and then it's right, this is kind of a yucky drawing, but this comes down to the middle, and then it makes a perfect right angle. That's why we call it a right pyramid. The base is a square with each side measuring 4. So all of these sides are 4. All right, I like it. The slant height of the pyramid is 5 centimeters. So again, slant height. You guys, this is how I can prove that we've had really long lesson 1 and lesson 2. My marker is already starting to die after 2 lessons. How crazy is that? The slant height is the edge. That's 5. Find the surface area of the pyramid. All right. So, and the slant height is not measured at the corner. It looks like it did. It's actually the middle of that triangle. I'm going to draw another picture of that triangle in just a second. So we'll clarify that. But let's get in here and see what we want to do. The surface area. Okay, that's where you add up all the sides. And just a second, I'm going to switch out to another color. I can't handle a fading marker. Okay. turquoise. Let me see, what's it really called? It's actually called Turquoise Surf. Oh, it's poetic, right? Okay, so let's do the square first. Right, that's so much paler compared. We're gonna do the square, and then we're gonna have 5 triangles, right? Oh no, I'm sorry, 4. I was looking at that 5 and my head went crazy. 1, 2, 3, 4, 1 coming up from each of the sides. If we opened this up and laid it flat, it would look like this, wouldn't it? So there's the 4 triangles and then the base. Okay, so the area of the base is length times width, and in this case it's 4 times 4. So the base is 16. What is our unit in this? Let me look back at the book. Centimeters. So this is 16 centimeters. I don't need to write it there, but it's 16 centimeters square. Now we need to find the area of the triangle. Okay, the area of a triangle is base times height divided by 2. All right, this is the base. How long is the base? Okay, it's 4. Right? Now, how tall, what is the height of this? Okay, that's where the slant height comes in, and that's why it's important to know that the slant height is not at the corners, it's in the middle of the triangle. So this is our slant height. It goes right down where we want it to, right? Because our little spider climbs up to the highest part of the triangle, drops a web straight down, and that's the height of the triangle. That spider test is what we can always do to make sure we're measuring the true height of the triangle and not just one of the sides. All right, so, and that is where the slant height goes. And let me clarify that again so you're 100% sure. The slant height is not at the edge where my original arrow looks like it's going. The slant height is the middle of the triangular panel, which you can more clearly see here. So that's good news because our slant height of 5 equals the height that we need for this calculation. We divide it by 2 because that's the formula, but then we multiply the whole thing by 4 because that's how many triangles we have. All right, let's see if we got that right. So now we can cancel these. We can cancel because everything's multiplication, we're fine. 4 times 5 is 20. 20 times 2 is 40. So each one of our triangles is 10 units squared for its surface area. All right, final step, we add them. 56 centimeters squared. John agrees with me. Yay. All right. So in this one, we learned how to use the slant height in a surface area calculation before we were doing volume. And we found out that it runs down the middle of the side. All right. Enough about cones and pyramids. Now we get to talk about spheres. Is this the last thing? Yes, this is the last thing, you guys. Hallelujah. Spheres. Spheres are 3-dimensional circles, right? And the way we often visualize them, okay, there's a circle. When I put these lines on it, that's meant to make it seem 3-dimensional to you. And when we want to find the volume on these little babies, what we do is we put them in a Pringles can. Just kidding, it's not really a Pringles can. But kind of. I'm drawing a perfect cylinder around it. Oh, darn it. Okay, I wish it was touching right there. It's meant to touch on the sides. That one looks much better, right? So what we've got is a single serving size of a tennis ball inside of its can. Everything's perfectly straight and even. It's packed perfectly tight so that there's no gaps between the tennis ball and the top of the can, the bottom of the can, and the sides of the can. All right, I tried to fix my drawing to make it look better. That is how we measure the volume of a sphere, is just like with cones and pyramids, we take the area of the base, which in this case will be a circle, we multiply it by the height, and we multiply that whole thing. Remember with cones and pyramids, we multiply it by 1/3. This time we multiply it by 2/3. Imagine that you're whittling the cylinder down, right? This is made of soap again, and we're whittling it down to get to this circle. We don't have to cut as much away as we did with the cones and the pyramids. This time we're only cutting away 1/3 of the soap, so that leaves 2/3. That's how I think of it. All right, let's do an example. Oh, I wanted to show you one other thing. So this would be the radius, right? Anywhere from the center to the outside of the sphere is going to be the radius. So the can is always going to be 2 times the radius in height, right? Because the radius goes from the center to the edge, then another one goes from the center to the edge, right? One to the top edge, one to the bottom edge. So 2 times the radius is always the height. All right, let's do a problem. 2.7, you guys, we're almost done. Just 2 more problems. You can tell how warped my brain has been by these long lessons, because I'm like, oh, just 2. Find the surface area and volume of a sphere with a radius of 9 meters. Okay, we have to do the surface area and the sphere. So let's review. We've got the volume of a sphere. Wait a minute. Second, I'm looking at my book with the light. Oh, I see. I want you to see what John does. What he does is he takes this formula and simplifies it a little bit, knowing that the area of the base is going, okay, so the area of the base is always going to be pi r squared, right? Because it's always going to be a circle. The height is always going to be 2 times the radius. So what he does is he takes this formula and he plugs those values in, pi r squared times 2r, right? Then what he does is he simplifies. So if you simplify this numerator, 2 times 2 is 4, r squared times r is r cubed, and then we have a pi left over, and then we have that as our denominator, okay? So this is a simplified version of this original formula that I gave you. See, we just plugged in those values and then simplified. So this is also an equivalent equation for the volume of a sphere. I like this one, to be honest with you guys, because I don't want to have to remember a new thing. Remembering the 2/3 is work enough, but having to remember the simplified version of it creates a new thing in my head. I'd rather remember this one, so I will leave it up to you to decide how you want to handle this. I'll work it with this version of the formula because that's what John does, and if you look back at the book, I want you to feel like John and I are doing the same thing, but this is a perfectly valid way to remember this. All right, so what we're going to do and our formula for the surface area John did the same thing, except he doesn't really show us. But this is the formula for, second, let me put, so these are the volume calculations, or yeah, the calculation of the formula. This is the formula for the surface area. I could show you how he got this, but at this point, your brain is overflowing. We'll talk about that another time. You can just trust me. This is the formula for the surface area of a sphere. It saves us a few steps. Okay, so now it becomes relatively straightforward to find the volume of this sphere that we're talking about that has a radius of 9. All we have to do is take this and plug it in. 4/3 times 9 cubed times pi. All right, 9 cubed, I don't know that right off the top of my head. 9 squared is 81 times 9, 729. Okay, so that's, this much is 729. Then we need to multiply it by 4/3, so I'm going to divide 729 by 3. 3 goes into 7 twice. Goes in there 4 times, and it goes in there 3 times. Okay, so that is dividing it. So now I have 4 times 243 pi. I stop and look, does John want me to multiply by 3.12, or can I leave my answer with pi? John leaves his answer with pi. Yay, that saves us a step. So now I just have to take 243 and multiply it by 4. Yes, I know you could do this faster on your calculator, but this exercises your brain, makes you strong. 4 times 3 is 12. 16, 17, 9. So the final answer is 972 pi meters cubed. That's the volume. A fairly straightforward calculation once we have our formula in place. Surface area. And we're just going to use this. It's 4 times pi times the radius squared, 81. So this one's even easier, right? John leaves the answer with pi, so we can say surface area equals, let's see, this is 324, right? I did 4 times 80 is 320. 4 times 1 is 4. And we're just leaving it pi. We're putting a unit on it. Surface area is a square. It's an area measure. So the moral of this story is that sometimes these surface area and volume problems are a long haul. Other times they're short and sweet. So don't be depressed every time you see the problems, because they might not be super long. Okay, ready for our last problem of this hideously long lesson? Oh my gosh, you guys have earned such a break. Example 2.8. Find the surface area of a sphere whose volume, okay, I'm writing down that it's a sphere, whose volume is 288 pi, and what's our unit? Centimeters. All right, we're supposed to find the surface area. This is another one of those problems where we have to take one answer, break it down into the components, and then use the component to find a different answer. So let's get our formulas in front of us. The volume of a sphere equals 4/3 times pi times r cubed. You guys will notice I don't always put the ingredients in the same order, but we're multiplying, so order doesn't matter. Surface area is 4 pi r squared. All right, so these are from the other page. You have them written in your book. That's information you already know. So we're going to start with this volume formula, and we're going to plug that in as the answer and solve it for R. So 288 equals 4/3 pi R cubed. All right. So what we want to do first is isolate the R cubed, right? So first, let's multiply it by 3/4, right? To get rid of this, we multiply by the reciprocal. Over here, 288 divided by 4 is 72. And then we multiply that by 3, and we get 216. Oh, I see what I did. Okay, hang on, let me just write this down. 216, and there should be a pi sign right there, right? I left that out of the original because look, there's the original volume of our sphere. So that should have a pi sign there. So I'm gonna put the pi sign in now. I forgot it before. So now, okay, so what we did is we got rid of this fraction first, multiplied by the reciprocal, simplified. Now we can divide both sides by pi, okay? And we get 216 equals R cubed. Then we're going to take the cube root of both sides. All right, this becomes R, that's cool. Now, what's the cube root of 216? I don't know that right off the top of my head, so I'll show you how we figure it out. I'm gonna take a wild guess first. I'm gonna start with 4 cubed because I know that one by heart. 4 cubed is 64, right? 4 times 4 is 16, 4 more. 5 cubed, I also know that one pretty well. 5 times 5 is 25. 25 times 5 is 125. Okay, so I know I'm headed in the right direction, but I haven't quite got there yet. How about 6 cubed? 36 is 6 squared. 36 times 6. (18, 19, 20, 21). There it is. So this is a method of figuring out a cube. I assumed it would be a perfect number because John is a buddy and a pal. But if I would have gotten a different number here and then gone on to 7 and realized it was too big, then I would have known, oh, it doesn't come out to an even number. But this one turned out to an even number. So we know now that the radius is 6 of this sphere that we're talking about. However, that's not the answer we're pursuing. John wants us to find the surface area. So, but now we've got what we need to find the surface area. So the surface area equals 4 times pi times the radius squared, which is 36. And so now we can multiply 36 times 4, 24, 144. (144 pi), what's our unit? Centimeters squared. Yay. This problem is a great example of you would work it through to here. Once you got 6 as the radius, I would stop and check this in the solutions manual and make sure I was on track. And then the last bit of the calculation is easy. Okay, you guys, that is lesson 2. I apologize. It's long and it's murderously difficult. There's a lot of information going on. It will get better, I promise. Every lesson won't be so long. Okay, so now, let me go back to this page that we did at the end of lesson 1. Okay, so hopefully by now you've done the odds and the evens for lesson 1. Now we're going to take the same approach to lesson 2. Do the odds on the first day, and then the evens on the second day. So by the end of the week, you'll have done all of both lessons 1 and 2. Good luck. Holler if you need help. Thank you for your patience.